If you're working in C, you know it's not just about writing code, right? You're negotiating with these two really powerful hidden forces. So today, we're jumping into a C programmer's survival guide for dealing with them. This isn't just about syntax, it's about mastering the relationship between you, your code, and the two guardians that actually bring it to life.
See, to really get good at C, you have to understand that you're talking to two completely different things at the same time. You can think of them as the two guardians of your code. Each one has its own personality, its own rules, and you've got to learn to speak their individual languages if you want to get anything done safely and, efficiently. All right, so let's meet our characters. On one side, you've got the compiler. The best way to think of it is as a super strict kind of pedantic teacher. Its whole job is to analyze your C logic, make sure everything makes sense, and it will absolutely give you a warning for every little thing it thinks is out of place. Then, you've got the preprocessor. This one's more like a clumsy but very literal robot. It has absolutely zero understanding of C. Its only job is to mess with the raw text of your code before that strict teacher ever gets a look at it. And believe me, that difference is critical. So let's start with challenge number 1, how to appease that strict teacher, the compiler. The goal here is simple. We want to write professional, clean code that doesn't spit out a whole flood of warnings every time we try to build it.
Now, the teacher's favorite rule is this. If you declare a variable, you create this little box to hold something, but then you never actually use it, the compiler is going to flag it. You can see the warning right there on the slide, unused variable, unused box. Now, sure, your code might still run, but in the professional world, warnings are basically treated as errors. The teacher is really just trying to help you keep your code clean and efficient. So how do you tell the teacher, hey, I know this variable isn't used and I did that on purpose? Well, there are two really common, kind of polite ways to do this. I like to call them the fancy sticker method and the I don't care cast. They're both just ways of officially acknowledging the unused variable, which honestly is all the compiler really wants from you. And each method has a place where it works best. Over on the left, you've got the fancy sticker, attribute unused. This is a special instruction, and it's perfect for function parameters that you might not actually need to use. And then on the right, we have the void cast. This is the one you'll see all the time for variables inside a function. It's basically you telling the compiler, yep, I see this variable, and I'm intentionally doing nothing with it.
And here's what that looks like in the real world with an unused argc parameter. That top arrow is pointing to the fancy sticker method right in the function definition. Or you could do what the bottom arrow shows and use the void cast inside the function itself. Both do the exact same thing. They tell the compiler you know what you're doing, and poof, the warning goes away. That's clean, professional code.
Okay, so we've made the teacher happy, but now we have to deal with the clumsy robot, the preprocessor. And let me just say, this guardian is way more dangerous. The teacher, it gives you warnings when you mess up. This robot, it can silently break your entire program, and you won't get a single hint that anything's wrong.
You have to get this 3-step process burned into your brain. First, you rate your code with macros. Second, the preprocessor robot comes in and does a simple, totally blind find and replace on your text. It has no idea what a variable is, or a function, or anything. And third, the compiler only sees the new, changed text. It has no clue your original macros ever existed, and that's exactly where the danger is. Okay, to make this really stick, let's use an analogy. Imagine your program is a delivery boy, just trying to get packages to the right addresses. The preprocessor is his friend, well-meaning but super clumsy, who insists on helping by rewriting all the delivery notes before our delivery boy even leaves the warehouse. And this is where the sabotage happens. Because the clumsy friend doesn't understand addresses or street names, just words, he rewrites the notes in a way that looks right to him, but is totally wrong. This messes up the order of operations. The delivery boy ends up at the wrong house, the package gets lost, and the whole system just fails. Your program breaks. That's a fun little story, but how does this robot actually sabotage our real code? What does this failure look like in a C program? Okay, check out this super common but super dangerous macro. #define square x, x times x. Looks totally harmless, right? You give it a number, it multiplies it by itself. Easy. But what happens when we give it an expression, like square of 2 plus 3? Now, we expect the answer to be 5 squared, which is 25. Let's see what our clumsy robot does.
And here it is, the syntax X-ray. Step 1, we ask for square 2 plus 3. Step 2, the robot does its blind find and replace and turns it into 2 plus 3 times 2 plus 3. And step 3, that's the trap. Because of the mathematical order of operations, multiplication happens first. So 3 times 2 gets calculated, which gives you 2 plus 6 plus 3. The final result? 11, not 25. Your program is now just silently, horribly wrong.
This kind of sneaky, dangerous bug is exactly why professional developers don't just rely on memory. To manage this clumsy robot, a modern workflow needs a safety net. And we can think of that as our AI Copilot.
Look, the clumsy robot is just too powerful and too literal to trust. So a modern developer uses tools, like an AI Copilot, that act as a shield. This tool can inspect what the robot did before it ever gets passed on to the strict teacher, catching these nasty little bugs before they can do any real damage. So what's the fix? How do we protect ourselves? The solution is parentheses, lots and lots of parentheses. The safe version of the macro is #define square x equals parentheses x parentheses times parentheses x. By wrapping every single argument and the entire expression in its own set of parentheses, we force the correct order of operations. Now, when the robot replaces square 2 plus 3, it becomes open parentheses, close parentheses, 2 plus 3, close parentheses, times open parentheses, 2 plus 3, close parentheses. The addition happens first, and we get the right answer, 25.
And this AI Copilot is way more than just a bug checker. Think of it like a whole toolkit. It's a safety inspector that automatically reviews your macros for these kinds of traps. It's a code generator that can write bulletproof, professional macros for you from scratch. And it's even a code archaeologist that can help you figure out what on earth those weird, complex macros you find in old legacy code are even supposed to do. So let's put this all together. Knowing what we know now about our two guardians, what is the modern, safe workflow for writing truly robust C code? It really boils down to 3 simple but absolutely essential rules. Rule number 1, satisfy the teacher. Always acknowledge your unused variables. Keep your code clean, keep it warning-free. Rule number 2, respect the robot. Never, ever forget that macros are just blind text replacement. Always think about how the text will look after the robot is done. And rule 3, deploy the Copilot. Use modern tools to check, generate, and understand macros. Never, ever trust that robot blindly. Ultimately, the most important takeaway here is that becoming a great C programmer isn't just about memorizing syntax. The real key is deeply understanding the personalities and the behaviors of the guardians who enforce the rules, the strict teacher, and the clumsy robot. By following these 3 rules, satisfy the teacher, respect the robot, and deploy your Copilot, you go from just writing code to actually engineering a robust, secure, and professional workflow. And with that, you can confidently hit that execution successful message every single time. So, what part of the C toolchain do you find the most treacherous? Let us know.